Hello everybody, I'm Lup from sunny Singapore. In this presentation, I shall talk about a fun new emulator for Apache NuttX RTOS, the TinyEMU RISC-V emulator. If you would like to download the presentation slides, please head over to this link, lubyuan.github.io/NuttX. That's the letter L, not the digit 1. My presentation, transcript, articles, and source code are available at that link. What if we could boot and test NuttX inside a web browser? Today, we shall talk about the TinyEMU RISC-V emulator that runs in a web browser, how we ported NuttX to the emulator, and how we customized TinyEMU to emulate the Ox64 single board computer by Pine64. TinyEMU is super helpful for running our daily automated testing of NuttX on Ox64. We will find out how it works. How did we make NuttX run inside a web browser? Let us explore the internals of the TinyEMU RISC-V emulator. TinyEMU sounds like a tiny flightless bird, but it is actually a bare-bones RISC-V emulator for 32-bit and 64-bit RISC-V. It runs in a web browser thanks to WebAssembly. And yes, TinyEMU runs Doom. And since it runs Doom, what about NuttX? Can we boot NuttX inside a web browser with a little help from TinyEMU? We are looking at the live website for Apache NuttX RTOS. Click the link for online demo, and we will see NuttX booting right inside our web browser, all thanks to WebAssembly. This is a great way for anyone in the world to experience NuttX for themselves, right within their web browser. And yes, OS test works great too. This is proof that NuttX runs incredibly well on all kinds of devices, including web browsers. The demo we just saw is live on the Apache NuttX website. Try it here, or head over to the NuttX website and click Online Demo. How did we make this work? In this presentation, we talk about the HTIF console that is natively supported by TinyEMU and how we modified NuttX to support it. This is the Berkeley Host Target Interface, HTIF. For console input, TinyEMU supports VirtIO console. We switch on the NuttX driver for VirtIO console, which calls the OpenAMP library for I/O messaging. This is for Open Asymmetric Multiprocessing. Then we compiled everything from C into WebAssembly with the Nscripten compiler. Why are we doing this? Well, it is kind of fun to watch NuttX run inside our NuttX website. Like they say, eating our own dog food. Later, we will talk about emulating a real RISC-V single-board computer. This is the Ox64 BL808 SBC by Pine64, which is super helpful for testing new NuttX apps and NuttX drivers. Maybe someday a NuttX dashboard that lights up and blinks in real time as the various NuttX drivers and NuttX apps activated. We could have done this in QEMU Emulator, though it is a bit too complex to customize. TinyEMU is tiny, easy to modify, and runs in a web browser. To prepare TinyEMU Emulator for modding, we download the C source code for TinyEMU, and we do the make. That is all we need. There is a demo of Linux booting on TinyEMU in case we need to figure out the internals of the emulator. We begin by customizing TinyEMU for the command line, then compile everything to WebAssembly later by calling the Nscripten compiler. We begin by setting the RISC-V system memory map in TinyEMU. TinyEMU is hard-coded to run at these RISC-V addresses. Yep, it is a very simple RISC-V emulator that doesn't have any fancy configuration files. We take NuttX for QEMU Emulator for 64-bit RISC-V. We see that NuttX is already configured to boot at address 80 million hex, so no changes required to run on TinyEMU. How do we actually boot NuttX on TinyEMU Emulator? We create a TinyEMU configuration file, which will start the 64-bit RISC-V emulator and boot it with our NuttX kernel. We try booting NuttX in TinyEMU, but nothing happens. Well, it didn't crash TinyEMU, which is a good thing. Remember that TinyEMU uses HTIF console, which NuttX knows nothing about. Let us teach NuttX to print something. NuttX is actually booting in TinyEMU Emulator, but we can't see anything because NuttX doesn't understand how to print to the TinyEMU console. Let us help NuttX now. TinyEMU supports HTIF for console output. This is the Berkeley host target interface. HTIF comes from the olden days of the RISC-V Spike emulator. HTIF is a UC Berkeley standard, not a RISC-V standard. We don't see it much in other emulators. TinyEMU source code is surprisingly readable. Here is the code in TinyEMU that handles HTIF commands. To print the digit 1 to the HTIF console, we set the device to 1, command to 1, the buffer to 31 hex. We write this long value to the HTIF register located at this address, like this. Now we understand how HTIF console works. Let us print something in our NuttX boot code. Our NuttX boot code is in RISC-V assembly. Thus, we write this RISC-V assembly code to print to the HTIF console in TinyEMU. And we see 1, 2, 3. Yay! Indeed, NuttX is running on TinyEMU Emulator. Okay, our NuttX boot code is printing something in RISC-V assembly. What about the UART driver in NuttX? Can we print the boot log and crash dumps? Remember we took NuttX from QEMU RISC-V, which runs on 16550 UART driver. Let us do a tiny tweak so that we will see something in TinyEMU's HTIF console. We patch the 16550 UART driver like this to make it print to HTIF console. What happens when we run this? We see NuttX booting OK on TinyEMU. Here is a NuttX boot log. But NHH shell doesn't appear. Why? Because NSH shell is a NuttX user space app that needs proper serial I/O with UART interrupts. In NuttX, serial output is buffered. It needs a UART interrupt to flush the buffer, which means NuttX will fill up the output buffer, wait for the transmit complete interrupt before sending more output. However, HTIF console doesn't support interrupts. Thus, we upgrade to a proper console with interrupts, VirtIO console. We have been doing console output with the HTIF console in TinyEMU. Won't it work for console input at NSH shell? Well, HTIF console supports polling of input and output, but it doesn't support interrupts. HTIF console is kind of bare bones, a bit like OpenSBI console. Polling only, no interrupts. To do proper console input and output with interrupts, we need VirtIO console. What is VirtIO? VirtIO is a standardized interface that allows virtual machines to access consoles, storage devices, and network adapters. And it works with TinyEMU. somewhat like RISC-V semi-hosting, but a bit more sophisticated. What about VirtIO on NuttX? Good news, VirtIO is already supported by NuttX. NuttX provides VirtIO drivers built with the OpenAMP library. That's the library for Open Asymmetric Multiprocessing. OpenAMP provides the message queue library for VirtIO guests to call VirtIO hosts by sending device messages. In this diagram, VirtIO guest is NuttX, and VirtIO host is TinyEMU. OpenAMP sits in the middle. Now, how do we make NuttX talk to VirtIO in TinyEMU? We look inside the TinyEMU source code. We see that TinyEMU uses these addresses for VirtIO. We copy these VirtIO settings to NuttX. With these settings in NuttX, the VirtIO drivers and OpenAMP library will start correctly on NuttX. This says NuttX has validated the VirtIO magic number from TinyEMU, otherwise NuttX will halt with an error. Yep, NuttX has detected the VirtIO console in TinyEMU, and the VirtIO device is 3. The NuttX VirtIO driver is talking OK to TinyEMU. Let us send some data to VirtIO console. To do that, we need 2 VirtIO queues, the transmit queue and the receive queue. This is how we create the VirtIO queues in NuttX kernel. Transmit queue and receive queue. We will message these queues, which will print to the console. But isn't there already a VirtIO console driver in NuttX? Yeah, NuttX has a VirtIO serial driver, but we will do it ourselves anyway, so we can learn the inner workings of VirtIO and OpenAMP. To print something, we send a message to the transmit queue, like this. Our code prints successfully in TinyEMU. All these virtual queue functions, they come from the OpenAMP library. So VirtIO in NuttX is tightly integrated with the OpenAMP library. Now we understand VirtIO and OpenAMP a little better, we can switch back to the VirtIO serial driver that is already in NuttX. We are almost done with NuttX for TinyEMU Emulator. Here are the remaining bits that we completed. We switch over to the official NuttX driver for VirtIO Serial, which will support console I/O with interrupts. For RISC-V interrupts to be triggered correctly, we set the PLIC address in NuttX. That's the platform level interrupt controller. We will keep the HTIF console, but only for printing debug messages during NuttX startup. There is something odd about RISC-V interrupts in TinyEMU. Somehow, TinyEMU won't let us enable MEIE, machine mode external interrupts. Our workaround is to enable SEIE, supervisor mode external interrupts. Then we patch the NuttX exception handler and map the interrupts from supervisor mode to machine mode. Nothing appears when we type in NH shell. Why? That is because we haven't enabled the echoing or key presses. Here is the fix. This will echo all keys pressed, and if the key press is carriage return, convert it to line feed. With these final few fixes, NuttX boots on TinyEMU Emulator all the way to NSH shell. We compiled TinyEMU from C to WebAssembly with the Enscripten compiler. Today it is live on the Apache NuttX website. Try it here, or head over to the NuttX website and click Online Demo. We haven't upstreamed the TinyEMU port to NuttX mainline. Let me know if you can help. This is a fun, impactful way to create something useful that anyone in the world can use by clicking the Apache NuttX website. If we look back at NuttX for TinyEMU Emulator, we tweaked NuttX to run on TinyEMU, which is kind of backwards. Why not tweak TinyEMU to emulate a real NuttX device? Then we can run NuttX on TinyEMU without any changes. Now we talk about TinyEMU emulating a real RISC-V single-board computer, the Ox64 SBC by Pine64, based on the Buffalo Lab BL808 SBC. This means we shall port NuttX for Ox64 directly in our customized TinyEMU emulator without any changes to NuttX for Ox64. We have a huge presentation on NuttX for Ox64 SBC. Please check out the presentation at this link. Today we shall chat about emulating the Ox64 SBC with a customized version of TinyEMU Emulator. Here is a quick peek of Ox64 Emulator. It runs the same way as the TinyEMU Emulator on NuttX website, except that we customize TinyEMU to emulate a real Ox64 SBC, and it will boot NuttX for Ox64 without any modifications, which is a terrific way to test new NuttX drivers and apps. Now we go into the details, how we customize TinyEMU Emulator to emulate a real Ox64 SBC. First thing we tweak in TinyEMU, the system memory map for Ox64 SBC. TinyEMU is hard-coded to run at fixed RISC-V addresses. Thus, we change these addresses to match the Buffalo Lab BL808 SoC. This part looks similar to the earlier slides, but instead of tweaking NuttX to run on TinyEMU, now we tweak TinyEMU to run NuttX. See the difference? The TinyEMU boot code is located at this address, 10,000 hex. It jumps to the NuttX kernel at startup. We will customize this for Ox64 SBC. Remember that TinyEMU supports VirtIO console. This won't work with the Ox64 SBC. TinyEMU needs to emulate the BL808 UART controller inside Ox64. We dig around the BL808 SoC and we discover these UART registers. We write to this UART register to print a character to UART output, and we read this UART register to check if UART transmit is ready for more output. This means that TinyEMU needs to intercept these UART addresses to emulate the BL808 UART controller. Inside TinyEMU, we intercept all reads to this UART register address and writes to this UART register address. That is how we pretend to be a UART port. More details coming up. This is the address of the UART status register. NuttX will read this UART register to check if UART controller is ready to transmit more output. In TinyEMU, we intercept all reads to this address and return the value 32. Why 32? That is the UART buffer size for BL808 SoC. It sounds simplistic, but it works for now. This is the address of the UART output register. NuttX will write to this UART output register to print a character to UART output. In TinyEMU, we intercept all writes to this address and we print the character that's written to the address. Don't forget the UART interrupts, which will be managed by the PLIC, Platform Level Interrupt Controller. To handle UART interrupts, we emulate these UART registers. UART status register should say there's UART input. UART interrupt mask should return 0. UART clear interrupt should clear the interrupt. UART input should return the key press. And we are done with UART. When we boot Ox64 NuttX on TinyEMU, we will see the UART interrupts handled correctly by the platform-level interrupt controller. TinyEMU boots NuttX in RISC-V machine mode, but we need TinyEMU to boot in RISC-V supervisor mode. Let us figure out how. What exactly is this boot code in TinyEMU? Think of it as BIOS for booting a computer. TinyEMU needs a tiny chunk of RISC-V machine code that will jump to a NuttX image in RISC-V machine mode. This won't work for Ox64. We will find out why. TinyEMU is a bare-bones RISC-V emulator. It boots in only one mode, RISC-V machine mode, which is the most powerful mode in the RISC-V system. But NuttX for Ox64 won't work in RISC-V machine mode. It expects to run in RISC-V supervisor mode, which is one level less powerful than machine mode. Why supervisor mode? That is because RISC-V SBCs, like Ox64, will boot OpenSBI in machine mode. This is the supervisor binary interface. It is like BIOS for RISC-V. OpenSBI then boots the NuttX kernel in supervisor mode. Okay, technically OpenSBI boots the U-boot bootloader followed by NuttX kernel. This means we need to tweak TinyEMU to boot NuttX in supervisor mode instead of machine mode. And we don't have OpenSBI in TinyEMU, so our BIOS for RISC-V is kind of absent. Hence, we emulate OpenSBI in TinyEMU, just the bare minimum of OpenSBI that is needed by NuttX, like for handling system timers. Remember the TinyEMU boot code we saw earlier? It boots our NuttX kernel in machine mode. Now we modify the TinyEMU boot code so it boots NuttX in supervisor mode. First, we dedicate all exceptions and interrupts so they get forwarded to NuttX in RISC-V supervisor mode instead of machine mode. Otherwise, exceptions and interrupts will whoosh by and bypass NuttX altogether. We are about to jump to NuttX kernel in supervisor mode. The way we do this is rather roundabout. First, we set the previous privilege level to supervisor mode, and we can execute an mret return from machine mode that will jump to the previous privilege, which is supervisor mode. We solve our headache. TinyEMU boot code now boots the NuttX kernel in supervisor mode. What about the RISC-V system timer? How do we emulate OpenSBI so that system timers will run correctly on NuttX? RISC-V system timer can only be set in RISC-V machine mode. NuttX runs in RISC-V supervisor mode. That is why NuttX expects to call OpenSBI to start a system timer through an eCall system call that will jump to machine mode. To emulate OpenSBI, our modified TinyEMU will intercept the eCall made by NuttX and set the system timer for RISC-V machine mode. NuttX expects to read the system time through the time CSR register, like this code from NuttX kernel. CSR means control and status register, controls a RISC-V system. We have a problem. The time CSR register doesn't exist in TinyEMU. Thus, we emulate the register in TinyEMU. At startup, we search for all RD time instructions. We patch RD time to become an eCall system call, and TinyEMU will emulate the eCall to return the system time. We have a few more steps to emulate the system timer. I won't cover the details today. Please check out these links. We talked about emulating the time CSR register because TinyEMU doesn't support it. Is there anything else that TinyEMU can't handle? Yep, inside the BL808 SoC is the T8C906 CPU. NuttX for Ox64 will call these special RISC-V instructions to flush the memory cache for the C906 RISC-V CPU, dcache.il and sync.s, which come from the T8C906 extensions and won't work in TinyEMU. Thus, we patch these special RISC-V instructions to become eCall system calls, so they won't crash the TinyEMU emulator, though we don't emulate the instructions right now. We talk about these special RISC-V instructions in my presentation on Ox64 SBC. Please check it out at this link. Our Ox64 emulator works great for emulating the UART controller and GPIO controller inside Ox64 SBC. Here, we run the QuickJS JavaScript engine on Ox64, which will blink a simulated LED connected to our emulated GPIO controller. We have a presentation that explains how we ported JavaScript to NuttX. Please check out the link below. We wrap up today's presentation with a super helpful way of using our Ox64 emulator. That is for daily automated testing of NuttX on Ox64. Let us walk through the implementation of the automated testing based on expect scripting and TCL. Yes, the good old scripting language. This gets triggered every day by GitHub Actions and alerts us via email if the daily test fails, which is terrific for NuttX regression testing. What exactly is an expect script? With an expect script, we can feed our commands automatically into the emulator. Here is an expect script that sends the uname command to our Ox64 emulator. If the NHH prompt is missing, or if the uname command takes too long to execute, this expect script will fail. Our expect script runs automatically like this. Will it work for complicated tests? Yep, that is the beauty of TCL scripting. We may use pattern matching and timeout detection in our script. It works really well with OS tests for testing everything in NuttX. And this is exactly what we do every day at GitHub Actions. Run OS tests on Ox64 emulator and fire us an email if OS test fails on Ox64 emulator. How thorough is OS test for testing everything in NuttX? Super thorough. Last we checked, these are the NuttX tests executed by OS test. Today, OS test has probably added a few more NuttX tests. Running daily automated tests on Ox64 emulator is probably the next best thing to running daily tests on a real Ox64 SBC, which we might try next. One final word on emulators. Recently, I'm so hooked on running good old games, Pac-Man, Collection, Street Fighter, on the retro gaming emulator like RetroArch, which got me thinking. RetroArch will actually emulate a couple of interesting architectures like ARM32, Z80, X64. What if we could run NuttX on RetroArch? Then we will have NuttX on RetroArch on iPhone, iPad, and Apple TV. As we ported NuttX to TinyEMU and created the Ox64 emulator, we wrote plenty of detailed notes. Check out the articles here. We have 2 more presentations on Ox64 SBC about porting NuttX to Ox64 SBC and the analysis of real-time logs from Ox64. Please check out the presentations at this link. The great news, our NuttX website now runs NuttX. Anyone in the world can click into our website and try out NuttX for themselves. We created an emulator for Ox64 SBC that is super helpful for automated daily testing and regression testing. Maybe we can create more emulators for NuttX devices and make NuttX development a little easier. Thank you.